Welcome everyone to the driven harmonic oscillator. Okay, so this is the second part of the harmonic oscillator series of videos. The previous one was about the free harmonic oscillator, where we saw how to get the equation of motion for a harmonic oscillator. And we actually computed what the solutions were like when you get a harmonic oscillator that is not driven by any force. You start with some initial condition and you let it go. And we studied the different regimes that the harmonic oscillators can have. Underdamped, critically damped, and overdamped. Now, today, we're going to see what happens when we drive it, when we keep applying a force. Think of a string, and then we apply a force periodically. A force in particular, but then it could be any force, but for this, we're going to focus on an external force that oscillates in time. In particular, we're going to consider a force that depends on, that oscillates with some frequency omega. This is what people, when you sing and you make a glass vibrate, that's what you're doing. You go like, you vibrate like, and then, well, actually I'm not doing a pure harmonic. Pure harmonic, a closer tone to a pure harmonic would be, but still nothing like a pure harmonic because my voice is not a pure harmonic. We will learn more about what I mean by a pure harmonic when we study Fourier analysis, but let me say pure harmonic is making, in this case, vibrate the air with a single frequency component instead of many frequencies. Now, but imagine when singers do that, they can actually get pretty like single harmonic, as in, like we call it monochromatic, only one frequency. When they sing to a glass, that's what they're doing. Then applying a force, the glass starts vibrating with the air, and vibrates because you apply a force periodically in time. And you all have seen how people can break glasses sometimes, and that's related with a phenomenon called catastrophic resonance. And we will study the phenomenon of resonance. So what happens when you actually drive? You see, you know, with a string, you know, right? You push, but if you push at a given frequency and it doesn't coincide somehow with the frequency of the oscillations, you may be even slowing it down for a while, right? But if you actually drive at the right frequency, you can kind of amplify the oscillations and make them grow in amplitude. We will see all that. All right, so we have an external force on top of the other forces that we had, which were the elastic force and the friction force. And we write the equation of motion that comes from Newton's second law like this. Remember this, here is the reduced force, right? We divide everything by the mass and it cancels. So this is the mass of the particle. I put it there just so the external force I can write in terms of the reduced force. F is the amplitude of the force, how strong you're applying the force at the maximum. And this cosine of omega t is a force that oscillates in time, being positive and negative alternated in time, okay? So, I'm driving the harmonic oscillator with some force that is like, you can tell intuitively that if I drive it with the right frequency, I'm going to be amplifying the oscillations, right? We'll see. The first thing that we realize is that, okay, what kind of differential equation is the driven harmonic oscillator? Well, it's a linear, second order, constant coefficients, non-homogeneous harmonic differential equation. And that means that we know how to solve it. We know that the solution is x of t will have the solution to the homogeneous problem plus a particular solution of the non-homogeneous problem. Now, let's remember what the solution to the homogeneous problem was. Remember what it was? We had three cases. We had the underdamped, right, which the solutions were like this, exponentially suppressed oscillations, right? We had the critically damped, where we have exponential suppression and no oscillations at all. And we have, this is time, of course, the x-axis, so this is x. And we have the overdamped, overdamped, which is, again, no oscillations at all, but even takes longer to decay, exponential decay anyways, but takes longer than the critically damped. Now, what these three solutions have in common is that they all are exponentially suppressed. You see, these solutions are exponentially suppressed. So what happens with the limit of t going to infinity, the long time limit of the homogeneous solution? That is 0. It disappears in time. So the homogeneous part of the solution disappears in time. We call this actually a transient. You have definitely heard that word. A transient is a part of the solution that disappears in time. And it's what happens, and it disappears in time because you have friction, and when you have friction, the friction will kill the transient. How interesting, right? What about the particular solution? The particular solution, if you remember the methods that we use to find the particular solution is, well, let's guess, the solution is going to look like the inhomogeneity. So the solution here will look like a cosine of omega t. Because you see, there's no, even in this case that is oscillated, the solution is not a cosine, it's an exponential times a cosine. So it means that this solution will never overlap with any of the homogeneous solutions. The solution, the particular solution, will look like an oscillatory function that is not suppressed in time. So that means that the particular solution will not die in time. So the limit of the particular solution for the long time regime, if you wait enough, is different from 0. So these two behaviors put together mean that if I actually take the long time limit of the full solution, the long time limit of the full solution is going to look like the particular solution exactly. And that's what we give the name here, steady state response. So you see, the solution will have two components at the beginning, a transient plus a steady state response, but the transient will disappear because it's exponentially suppressed. So if somebody asks you, for the long time behavior of the driven harmonic oscillator, what is more important, the homogeneous solution or the particular solution to the non-homogeneous problem? You should say, aha, the particular solution to the non-homogeneous problem, because that is the one that will survive in the long time regime. All right, that's clear. Okay, let's find what the solution would be like. Let's find what the steady state response of this oscillator will be like. Again, if you started, you start and then you start from some outside equilibrium position, you start forcing, they will have this transient, the transient will disappear. What is the steady state response like? Now, we could do it in two different ways. We could do it by using the method that we learned before, but that's fine, you've already practiced that in assignment. Let's do it with a method that is like, I mean, it's similar, it's actually the same method, but let's use a little bit of complex calculus to try to make it easier, shall we? All right, let's erase the board. So, I have the equation I want to solve, I want to find a particular solution for, and I made up a new equation. Look at it, isn't it cute? This equation looks a lot like the first one, with one difference. The function is called y, and I multiply the whole freaking thing by I, by the imaginary unit. Why would I do that? Well, say that I combine the equation that I'm interested in actually getting the solution for, the particular solution, and this one, I combine them, adding up. I sum the two of them. If I sum the two of them, I get x, so let me call this one 2, and this one 1, and let me write 1 plus 2, and we get x dot dot plus iy dot dot plus twice psi omega x dot plus iy dot, right, plus omega squared x plus iy equals f that multiplies I sine omega t. Well, in fact, let me put the cosine first because that's the order I was following, just for aesthetic purposes. Cosine of omega t plus I sine omega t. Cool, all right, so if you remember your basic complex calculus, you would remember, I mean, if I were taking this really, really seriously, there would be a card there linking to the complex introduction, but whatever. This thing is e to the I omega t. Aha. So, if I define a new variable, let me do a change of variable from x and y to a complex variable z, x plus iy. Look what I can write. What I can write is, so remember, doing that I know that the real part of z is what I'm looking for, is x, right? Okay, if I do that, what I get here, this is z squared, right? Let's just write it for fun. This thing is, so we have z dot dot, this is z dot, this is z, so the equation I have is z dot dot plus twice psi omega, z dot plus omega squared, z equals f exponential of I omega t. And that is pretty cool because it allows me, instead of doing a trigonometric substitution for the particular solution, I can do an exponential one that is way easier. All right, I need to make a guess. The guess for the exponential, if it were a real exponential, the guess for z particular, right? Remember, the guess was e to the, let's say the exponential of I omega t. It would be something like I omega t. But keep in mind, this is two variables. This is a complex variable, a real and imaginary part. We need two constants. The other constant, we put it there. Okay, it's a phase. We have a constant that is the amplitude and another constant to determine that is the phase. Without this constant here, maybe I'll write it with a plus or with a minus. I mean, in the notes I have a minus, so I'll do it with a minus. Why not? Okay. It doesn't matter because it's an arbitrary constant. All right, so I have these ansatz. My ansatz for this solution is a e to the I omega t minus delta. All right, you see I need an answer for the real part, for the imaginary part, which is two variables. This is the same as doing an answer for the amplitude and for the phase. Remember the two solutions when you have the case that the roots are conjugate, a couple of the roots of the characteristic polynomial are a couple of conjugated roots, and you could write as a sum of a sine plus a cosine with two constants, or a sine multiplied by a constant plus the frequency t plus delta. This is similar, it's the same kind of thing. Alrighty. So what do we do now? We plug in this into the equation. If we plug it in, we get the following. Minus omega squared a plus I 2 psi omega big omega a plus omega squared a equals f to the e I delta. There we go. So I divided the whole thing by e to the I omega t minus delta. I divided the whole thing. So so basically you would get this multiplied by e to the I omega t minus delta. This one also multiplied by e to the I omega t minus delta, because this comes from the second derivative, this comes from the first derivative, this comes from the function itself. So all of them will have this exponential in here. You can cancel all of them by dividing by that. When you divide this term by e to the I omega t minus delta, you get a positive delta as a result, right? I mean, let me just write the last step. F e I omega t divided by e to the I omega t minus delta is of course the same as if f e I omega t, then e I omega t e minus delta. This cancels, and this is the same as f e to the minus delta. I minus, sorry. This and I missing here, minus I delta. All right, so that's what I did there. Okie dokie. So we have this equation that comes from inserting, this is a guess, this is an ansatz. We plugged it in and we obtain this equation, and we can simplify this equation and write this again as a cosine and a sine to make it easier. So this thing it's equal to, well, I'll write it again. We have minus omega square A plus I 2 psi omega A plus omega square A equals F multiplying the cosine of delta plus I sine of delta. And then what we do is, this has to be true for all values of omega and psi, which means that the real, well actually we have something complex on the left, something complex on the right. So the real part of the left has to coincide with the real part of the right. The real part on the imaginary part on the left has to coincide with the imaginary part on the right. We equate the two and we get real part. And the real part gives me, what is the real part here? Well, minus omega square A, this is imaginary, plus omega, that's the real part on the left. So A multiplying omega squared, that's the positive one, minus big omega squared on the left. And on the right is F times the cosine of delta. And the imaginary part, well, the imaginary part on the left is 2 psi omega A equals, that's not a minus, this is a typo, A equals, this is on the left, that's what multiplies the I. What multiplies the I here is F sine of delta. All right, so the first thing that we can do to find delta really quickly, we can divide, let's call this equation 3 and 4. And what I do now is I divide 4 over 3. If I do that, if I divide the two equations like that, I get the following. I get that on the numerator 2 psi omega, and in the denominator omega squared minus big omega squared. So that means that, and on the right, what do I get on the right? Well, on the right I get the cosine over the sine, so the sine over the cosine of delta, which is the tangent of delta. So that means that I can solve for delta. Delta is the arctan of 2 psi omega divided by omega squared minus small omega squared. All right, I found the constant delta. Wonderful. So let's find A. To find A, we're going to use the identity that we used before with the sine, and we're going to use the other version, the cosine of the arc tangent of x. It's equal also to 1 over 1 plus x squared. Remember that with the sine, we had a similar identity, but with an x in here, and with the cosine, we had it with a 1, okay? Remember, we used the identity before in a previous video. In the previous video, arc tan of x is equal to x divided by 1 plus x squared. Remember that? But we're going to use this other one, which is the cosine. All right. And you can tell, right, that these identities are true. How? Well, because if you actually do, let's do cosine of arc tan x squared plus sine of arc tan x squared. That should be 1, right? Because that cosine plus a sine all squared. That's cosine squared plus sine squared. But let's see. We get that this would be 1 over 1 plus x squared plus x squared over 1 plus x squared. So this is equal to is 1 plus x squared divided by 1 plus x squared equals 1. So indeed, the identities are, you can check they're correct. They're not made up. At least they satisfy the equations they have to satisfy, right? Anyway, this was just a fun note. We're going to use this identity, and let me clear the board a little bit. All right, so I cleaned the board a little bit, and I kept equation 5, which is the delta. I kept equations 3 and 4, moved a little bit down. the real part and the imaginary part, equations after inserting the answer in the equation, and I get the identity we're going to use. Now, what I did here is substitute equation 5, the value of delta, into 3 to find A, and you see we have f cosine of the arc tangent of this, and we can use this identity. So that allows me to find A. A is going to be f in the numerator, and in the denominator I have divided by that omega squared minus omega squared. And now this identity, which is 1 over root, so 1 over the root in the denominator of 1 plus x squared. So 1 plus 2 psi omega omega divided by omega squared minus omega squared squared. All right, wonderful. So what we have now, we can simplify. Actually, we can simplify both. What I'm gonna do, let me tell you the steps, and I'll tell you the final. I'm gonna put this in here. I'm gonna multiply this. This enters with another square inside, and that simplifies this one, and that's one term here. And then I'm gonna divide by small omega everything. So what I get, actually by small omega squared. So what I get is that A. Well, I'll do the two steps. First, A is 1 over root of omega squared minus capital Omega squared squared plus 4 times psi squared omega squared omega squared. That's what happened when I put this inside here. And now, and f of course. And now I can simplify one step further and get f in the numerator divided by omega squared. I divide by omega squared both sides, and I get in the denominator root of 1 minus omega over omega all squared plus 4 times psi squared omega over omega squared. All right, this is A. This is A, and this is the amplitude we're looking for. And we can do the same for delta. We can write delta in what we call dimensionless units. We can dimensionalize delta. Again, dividing, what I'm going to do, I'm going to divide by omega squared numerator and denominator here. So I get this expression for delta equals the arc tan of, and now we get the numerator 2 psi omega over omega divided 1 minus omega over omega squared. All right. Now, wonderful. So we found A and we found delta. Now we can find the solution, the steady state solution. Let's just substitute. Remember, we have an answer, and the answer was that Z is equal to A e to the I omega t minus delta. So we substitute the answer, and we take the real part, and we get the solution is the following. So let's do it. All right, so that's the particular solution that we found. But then again, this is a complex solution that we made up because we added a made-up solution that was imaginary. The real one, remember, comes when you take the real part of Z. So the physical solution, x of t, it's equal to the real part of Zp, right, which is equal to the real part of A of omega e to the I omega t minus delta. Now, what do I write of omega? Well, I wrote it also here. It's because it does depend on big omega, right? The amplitude that you reach in the steady state regime is a function of the frequency of driving. Remember, how often do I push the swing, okay? All right, that's very easy because the amplitude is real. So this is just A of omega, that amplitude over here, times, well, this is cosine of the argument plus I sine. So the real part is the cosine of omega t minus delta. All right, and this is my particular solution. All right, let me write it here. Let me just quickly move the solution over there. All right, so now that we have that, we can ask the following question. Okay, so now tell me, How often do I have to push the swing to get my kit the highest possible? How do I do that? What is the frequency of the driving that maximizes the amplitude? How do we do that? Well, we know how to compute that, right? We want the maximum of A as a function of big omega. So let's find the value of omega so that A of omega is maximum. All right, let's do it. So we equate the derivative to 0 to find the critical points. That's basic calculus. So let's write the derivative. It's a little bit long, but let's do it. 8 psi squared big omega divided by small omega squared minus 4 times omega 1 minus omega squared divided by small omega squared. This divided by omega squared. And then this thing divided by twice 4 psi squared omega squared divided by small omega squared plus 1 minus omega squared small omega squared squared to the 3/2. The derivative of a square root, right? All right, so, all right, fair enough. Now, we equate this to 0. That means that the denominator, I don't care. The numerator, I care. The numerator equated to 0, that will happen. I can actually cancel the omega squares, one of the omegas. I can divide by 4. So I get the following equation. I get that twice, oops, this is an arrow, twice psi squared plus omega squared divided by omega squared minus 1 equals 0. You see, that's the numerator. After simplifying, multiplying by omega squared both sides, divided by 4 both sides, and divided by big omega both sides. All right, wonderful. So that allows me to solve now. I can solve for big omega, and I'm going to call it res, that's the omega that gives me the maximum, is small omega square root of 1 minus 2 psi squared. That is the frequency at which I have to drive in order to get the maximum amplitude. If you want to get your kit the highest possible, you actually push that many times per second. All right? Now, notice that this is a function, is the natural frequency times this factor that depends on the damping ratio. So if there were no friction, the resonance frequency is the natural frequency of the oscillator. Okay, well, yeah, let's discuss, because we have mentioned the resonance frequency of the oscillator, which is this one. We have mentioned the natural frequency of the oscillator, that is omega. We also mentioned the frequency of free oscillations. What is all that? Let's summarize it and discuss it a little bit. All right, so there are, in what we studied, there are 3 different frequencies that we talked about that are important to describe the harmonic oscillator. So first, we have the natural frequency. The natural frequency is what appears in the equation of motion. It's called small omega, and it's the frequency of free oscillations if friction is 0. The damping ratio is 0, if there's no friction whatsoever. That means it's the frequency if I get the oscillator, if I perturb it a bit, I tilt it a bit, and then the thing starts oscillating, right? Like pull it a little bit and release, starts oscillating. If there were no friction, the natural frequency is the frequency it would oscillate at, okay? If there were no friction, in the ideal case that there were no friction. Now, we also talked about the frequency of free oscillations that we call in the notes omega d, also omega free, it's often used, which is omega times the root of 1 minus the damping ratio squared, and that's the frequency of free oscillations taking into account friction. So you perturb it a bit, you let it go, starts oscillating, and the frequency of those oscillations is this one, when there is friction. You see how when psi is 0 they coincide, all right? So the natural frequency is not the frequency of free oscillations, they're different, and the difference is because of friction. And then finally, we have the resonance frequency. The resonance frequency is the frequency of the driving that maximizes the amplitude of the steady state response. So at what frequency do I have to drive the oscillator in order for the amplitude at long times to reach the highest point? In other words, remember, the driving frequency, which is the omega here, is the frequency of the driving. Imagine a swing. In a swing, if I push the swing 1 time per second, the frequency is 1 hertz. It's exactly that frequency. How often do I push the swing? And the resonance frequency is the frequency at which I have to push in order for the kit to get the highest possible when it reaches the steady state, right? When it's like, okay, keep pushing and it reaches the steady state. The highest possible will happen when I drive at resonance, right? Okay, so now, these three different frequencies, you see that they coincide if there's no friction. If there's no friction, the natural frequency is the same as the frequency of free oscillations, and is the same as the resonance frequency. I guess that's the reason why in popular culture they confuse them all the time, because in popular, look, think of the case in which they break glasses, right? So they get the glass, they hit it first, and then here, and then the person says, okay, I'm gonna match that sound, and matches that sound and breaks the glass. People usually explain, yeah, when you hit it, that's the natural frequency of the glass, and then I drive at that frequency by singing at that frequency, and then I break it because it's resonance. Not quite. When you hit it, you don't get small omega, you get omega free. And then when you drive, in order to break it, you need to drive at a resonance frequency. But you see, those glasses are made of really good thin glass, friction is really small, and when friction is really small, the three coincide. So that's why maybe people confuse them, but keep in mind that you learn now that the natural frequency and the frequency of free oscillations and the resonance frequency, they're not the same, they're different because of friction, all of them, okay? And this is the one that you want to sing at in order to break the glass. The frequency of the pushes in order to get the kick the highest possible. The frequency of the signal source that you have in order to get the amplitude of oscillations in a LC circuit, the highest in an RLC circuit, the highest possible. All right, so let's see one little thing. What happens if I drive at resonance with no friction? Remember, imagine if the damping ratio is 0, then of course omega res equals small omega. And then the amplitude at resonance, when I evaluate it at resonance, which is small omega, is, well, this is 0, there's no friction, so the square cancels, and I get f over omega squared. And now I get 1 over 1 minus omega over omega squared. But this is small omega as well, because the resonance is when big omega is equal to small omega. So this thing actually diverges, goes to infinity. That is catastrophic resonance right there. So if you have a system that has very little or no friction, if you drive at resonance, the steady state response is infinite amplitude oscillation. You're gonna break the structural integrity of whatever you are considering. That's what happened with the glass. The glass has very little friction, so when you sing very high, you're gonna drive it at resonance. It's gonna start, the amplitude is gonna grow towards the steady state amplitude, and that steady state amplitude, if there's no friction, is infinity, and it breaks completely. That's catastrophic resonance. That's what happened with the Tacoma Narrows Bridge. You can Google, you can find the videos. It's quite impressive to see those videos. So you get gusts of wind that were actually hitting the bridge at a frequency, and it's because of the trees that were around in a forest that were like letting the gust of wind go in a frequency. It's like woo, woo, releasing them. And it so happens that by chance, the gusts of wind were hitting the bridge at the resonance frequency of the bridge. The bridge had very little friction. You have to build bridges with friction. Sometimes you want the freaking friction. You want to dissipate that energy. You don't want that energy to stay on the bridge and shake it. You want to dissipate it. What happened? The bridge had very little friction. So it was a case of catastrophic resonance. The amplitude grew too much, and you see it reaching the steady state. It takes a while. There's the transient and the steady state, and it's going towards the steady state. The bridge goes like that and eventually breaks. That is catastrophic resonance, and that's something that you have to keep in mind in systems design in general. All right, let's see all this in a computer, shall we? All right, we are now prepared to do a numerical demonstration of the phenomenon of catastrophic resonance. Well, resonance, and in particular, catastrophic resonance. Okay, we have here our driven harmonic oscillator equations. Here's the amplitude of the steady state response, so the height at which a kid would get in a swing that I'm pushing, right? The maximum amplitude at the steady state. Well, not the maximum, the amplitude at the steady state as a function of A0. A0 is F divided by omega squared, is basically the strength of the force that you're pushing, the strength and the normalized strength of the force that you're pushing, reduced. And then it's a function of the frequency of the driving, how often do I push the swing, the natural frequency of the oscillator, and the damping ratio. We have here the phase shift as well, and the amplitude. We're not going to use the phase shift for this demonstration. But let's just plot the amplitude. You see, the x-axis is big omega. The x-axis is the frequency of the driving,
So how often do I push the swing? And the y-axis is the amplitude at the steady state. So how high, what is the maximum height that the kid gets on the swing? You can tell that there is a maximum, right? There's a frequency that if I drive at that frequency, the amplitude at the steady state will be maximum. So you can tell if we ask for the coordinates of that, you can see that those coordinates are not exactly at 10, it's slightly below 10, and the reason why it's slightly below 10 is because remember the resonance frequency is not the natural frequency, that's a common misconception, it's the natural frequency multiplied by the square root of 1 minus 2 psi squared. So because psi is not 0, it's slightly below 10. Now of course if we change the natural frequency, the resonance frequency also changes proportionally to it, and that means that to get the maximum height I have to drive at this frequency. If I get close to resonance I could get pretty high, but it's at resonance where you get the highest. Now of course if let's put this at 15, which is a very manageable number, so if I increase the damping, if there's more friction, I don't get that high. The oscillations don't get that big, right? Even at resonance. But let's see, imagine that the swing has a tolerance of 5 units of amplitude. It can go 5 units that way, and then it breaks after 5 units, right? Or the glass that is vibrating, the walls can move 5 units. After that, the structural integrity is compromised. Let's see what happens when I start reducing the friction. As I start reducing the friction, the maximum amplitude increases, and at some point it gets above 5. At this point, it means that if I drive at any frequencies around resonance in this area, then I would break the glass. I would break the swing, and poor kid that is in the swing. Now, in fact, you can see how catastrophic it gets. As I remove friction, the whole thing gets catastrophically amplified at resonance, as you can tell. All right, so this is a demonstration of the phenomenon of resonance. Before we leave the topic of the harmonic oscillator, let's actually see how the harmonic oscillator is modeling an RLC circuit, and that would be the end of this topic.
All right, before we leave the harmonic oscillator, let's actually see explicitly why an RLC circuit is a harmonic oscillator. Of course, you're going to see plenty of this in your circuit course, but I think it's nice to compare one-to-one the equations of motion for an RLC circuit with an external source and the equation of motion of the harmonic oscillator to identify what is the friction exactly, the damping ratio, natural frequency, etc., etc. All right, so let's begin. So we have here an RLC circuit, and of course we know that intensity, current, as we would call it, it's the time derivative of charge, which is of course the capacitance time derivative of the voltage at the capacitor divided by T, right? It's a series circuit, okay? So the intensity, the current on the circuit is the same to all the elements, so we know that in particular we can write it as a derivative of the voltage on the capacitor. Now, of course, we also know that VR, the voltage fall in the resistor, it's IR, which is the same as RC, the voltage in the capacitor, derivative with respect to time. And finally, the voltage fall in the inductor is L di dt, and of course the same I for all the circuits. So we substitute and we get LC, second derivative of the voltage on the capacitor, divided by T squared. All right, we can now write Kirchhoff's voltage law around the only loop that we have in this circuit. And of course we get, let me write first the VL, and then plus the VR plus VC, okay? And of course equals to the external source, the signal that you input it into the circuit. All right, so if we substitute, we get the following equation. VL tells me that this is LC VC dot with respect to time, plus VR. Okay, VR is RC VC dot, right? And then finally plus VC, which is just VC, equals to V external. All right, so what we can do now, we can normalize this equation, and if we normalize this equation, we get the following. Let's do it. VC dot plus, we divide by LC, so R divided by L, VC dot, plus 1 over LC, VC equals V external, divided by LC. All right. And now, let's write right next to it, let's write the equation of a harmonic oscillator. X dot dot plus twice psi, I'll write a better psi, okay. My attempt to it, omega x dot plus omega square x equals the reduced force, the reduced external force, if you remember. All right, so that means that we can identify terms quickly. We can find the natural frequency of the circuit. The natural frequency of the circuit, comparing is omega squared, comparing these two terms, right? The zero derivative. The natural frequency of the circuit squared is 1 over LC. So of course, omega is 1 over root LC. That's the natural frequency of this circuit. We can also find psi, right? We substitute omega 1 over root LC and compare with this term, and we get that psi is equal to 1/2 R square root of C over L. So that is the damping ratio, of the circuits as a harmonic oscillator. And finally, of course, the reduced external force is the external signal divided by LC. All right, so you see how the friction is there because of the resistor, and the natural frequency is 1 over root LC. Now, you want to talk about resonance, and you can talk about the free oscillation frequency and so on. You can use all the knowledge that we have from the harmonic oscillator. This is only one equation. You can have other equations in terms of the voltage fall along the capacitor, and you can put an oscilloscope signal here, and then you will get the solutions for the harmonic oscillator that we saw. But there are many ways of looking at this harmonic oscillator. This is one of them. I hope you're gonna see all of them in your circuits course. I know it's a very good course, and the professor is really good. He will cover all this, but I think it's good to see it back to back. The harmonic oscillator, how it relates, how an RLC circuit is nothing but a harmonic oscillators. Harmonic oscillators are everywhere. All right, so this is all for the topic on harmonic oscillators. I hope that you enjoyed it. A little bit of connection of what we do with some physical systems that you are familiar with. The next thing we're going to see is actually how to solve equations using a tool called the Laplace transform. Laplace transform is going to be immensely useful because it will allow us actually to solve equations even when the coefficients are non-constant, when they're linear or non-constant coefficients and beyond. We will learn about it, so don't worry, we will actually learn the tools very well, and that will be in the next video, and I'll see you then. Have a good, the interval of time between now and when you watch the next video. Bye bye.